What is the maximum likelihood estimate? Let's see. So how do we create machine learning models? Let's take a model like an SVM or a linear regression model. So we first come up with a loss function which defines how our predicted values deviate from the actual values, and then we find those parameters of the model that minimize this objective function. Now, how do we come up with the objective function when the model is defined in a probabilistic fashion? Like, let's say logistic regression or the naive Bayes classifier. So for probabilistic models, we come up with an objective function by looking at the likelihood of the observed data given the parameters and find that parameter which maximizes the likelihood of what we have already seen. Let's see a little more in detail what this means. So in short, the MLE estimate involves finding the parameter that maximizes the likelihood of the observed data. Let's break up this sentence. What do we first mean by finding the parameter in a probabilistic model? So let's take a simple example. Suppose you look at the Gaussian distribution or the normal distribution that you all know. So we have probability of x is defined as 1 by root of 2 pi sigma square, the standard Gaussian formula. And it's a function of x, e power minus x minus mu whole square by 2 sigma square. The parameters of this model are the mean mu and the standard deviation sigma. Now, if we are given a bunch of points that are generated from this Gaussian, the problem of parameter estimation involves finding the best value of mu and sigma that makes sense given the points that we already have. So let's look at another example. Let's say we have a Bernoulli distribution, which could represent the probability of a head when you toss coins, let's say. So let's say you're tossing some coins and define the probability of heads as p and the probability of tails as 1 minus p. This is the Bernoulli distribution. What is the parameter here? The parameter is p, the probability of success. So now with the maximum likelihood estimator, we want to find again the value of p that maximizes the likelihood. So suppose we see 4 heads and 2 tails. What is the value of p that makes most sense? The MLE can do that. Let's look at another last example. Let's take the example of logistic regression. So here we have probability of success defined as a sigmoid function of W transpose x plus b or AX plus b. And the sigmoid itself is defined here. So what are the parameters here? The parameters are a and b. Now, if we are given a bunch of points, features and target labels, we want to find the best value of a and b that make the data possible, whatever we have seen, right? That make the data that we have seen most likely. Okay, so this is what we mean by finding the parameters. Now, what exactly is this likelihood that we are talking about? How do we define it? Now, for this, let's again go back to the example of coin tosses and Bernoulli distribution. And it's the same whichever example you take. Let's say you toss a coin n times. So the observations are x1, x2, x3 up to xn. So this could be like heads, tails, tails, heads, and so on. The likelihood of the data is nothing but the joint probability of these observations. So we have the likelihood of data is the probability of x1, x2, x3 up to xn taking the values that you actually saw. So that is nothing but probability of x1 being what you saw, x2 and to probability of x3 into probability of xn. Because these variables x are identically distributed and are independent. They are called IID variables. So this is the likelihood. It's nothing but the joint distribution of the observed data, the joint probability of the observed data. So suppose you have 4 coin tosses and you saw heads, tails, tails and heads, which can be denoted by 1, 0, 0 and 1. So what is the likelihood? Let's compute. So probability of x1, x2, x3 and x4 is probability of x1 into probability of x2 into probability of x3 into probability of x4. So probability of x1 taking 1 is p based on our Bernoulli distribution. Then x2 being 0 is 1 minus p. x3 being 0 is 1 minus p. x4 being 1 is p. So we end up with p square into 1 minus p square. This is the joint probability of the observations, and this is nothing but the likelihood of our data. As you can see, the likelihood is a function of the parameter p that we are trying to find out. So the question now we have is, we have head, tail, tail, head. What is the most likely value of p? And the likelihood is p square into 1 minus p whole square. So now, if we have n coin tosses in general instead of 4, we would have likelihood given data x1 to xn is p power small n into 1 minus p power capital N minus small n. So small n is the number of heads and capital N minus small n is the number of tails. So if we have 2 heads and 2 tails, this becomes p square into 1 minus p square. Right? So, okay, now what do we mean by maximizing the likelihood? So we saw what the likelihood function is, and it's a function of the parameter p. So in general, if you plot the likelihood as a function of the parameter, what value of the parameter gives you the maximum value of the likelihood? You want to find this value of the parameter. How do you do that? So now we can think of this as a standard optimization problem, because we have this objective function p power n 1 minus p power capital N minus small n, and we want to find argmax of this with respect to the parameter p. Find that value of p that maximizes this. How do you do this? So the first thing we can note is that the maximum value of the function, the value of p that maximizes the function, will be same for that which maximizes the log of the function. So we can take a log of this expression and then expand it out. So now we have an equivalent objective function in terms of the log. That's called the log likelihood, in fact. And if you recall your basic calculus, in order to find the maxima or minima, you need the first derivative to be 0. So we take the first derivative with respect to p, the parameter, and equate it to 0. And we get an equation like this when we do that. So we get n by p minus capital N minus small n by 1 minus p equals 0. And if we simplify this, we end up with p equals small n by capital N, or the number of heads by the total number of tosses. Right? So if we take the data 1, 0, 0, 1, we end up with p equals 2 by 4 or 1 by 2. Now, as you can see, it's not really rocket science to infer that the value of p is probably half if you saw 2 heads and 2 tails out of 4 tosses. But what the MLE estimate is trying to do is to tell us the math behind this common sense answer that we come up with. In a similar fashion, suppose I gave you the Gaussian distribution that we had before, a bunch of points taken from the Gaussian, and I ask you to estimate the mu parameter or the mean parameter of the Gaussian. If you do all this math for maximum likelihood estimate, that is, you write down the likelihood and maximize it and find the value of mean that maximizes the likelihood, you'll just end up with a sample mean, which is the sum of all the points divided by the number of points. So very often we get a very intuitive answer with the maximum likelihood estimate. So some more things about the MLE estimate. For more complex models, we can solve for the MLE estimate using gradient descent or other optimization algorithms, because simple differentiation might not lead to a direct closed form solution. So if we differentiate it and equate it to 0, it might not give us directly a closed form solution. Another point to note about MLE estimate is that the more data we have, the more we can trust the MLE estimate. In mathematical terms, it's called asymptotically unbiased. But what this really means is that as we have more data, we can be more confident about the MLE is more likely to be closer to the actual value of the parameter that we are trying to find. So just to again put this in perspective, what are some models that actually use this kind of an MLE estimate to sort of put it back in perspective with what we know? So Some of the models you might have seen are logistic regression, the naive-Bayes classifier, or Gaussian mixture models and hidden Markov models. So these are all these can be solved using the maximum likelihood estimate, the parameters of these models. So once again, let's recap what we have seen. We have seen what the maximum likelihood estimate is and why we care about it. We have seen how one can actually find parameters of a machine learning model by writing down the likelihood of from the data and finding that parameter which maximizes the likelihood of the observed data or the existing data. So hope this is helpful. Thank you.